Here's part 2 of all of grade 9 math in 60 minutes or less. So hopefully you've watched part 1, the algebra unit. We've got about 25 minutes left to get through the rest of grade 9. This section will be shorter than the algebra section, and the last section, geometry, will be the shortest section. So this is part 2, linear relations. Once again, I'm going to go quickly through the concepts and just a few examples of things. If you want more in-depth explanations, go to jensenmath.ca. There's videos for each section there. Okay, so here we go. Linear relations. So first thing you would have looked at probably is scatterplots. Scatterplots is a type of graph that shows the correlation between two quantitative variables. So for example, we have two variables here, year and movie attendance in millions, and this is Canadian data. So we have two variables. It's important to understand the difference between the independent and the dependent variable. If we have a table of data that's in horizontal rows like this, x, our independent variable, is usually the first row, and y, our dependent variable, is usually the bottom row. It's important to know the difference between the two variables because that determines where we put the variables on our graph. The independent variable goes on the horizontal axis, dependent on the vertical axis. And also, so independent variable is year in this one. Dependent variable is movie attendance. And another way to tell which variable is which is that attendance depends on the year, so that makes it our dependent variable. The year causes a change in the attendance is another way to think about it, so that makes it our independent variable. If you're given data in vertical columns, remember that x is usually given to us on the left, so independent on the left, y on the right. And when we graph it, make sure you remember that we are going to put our independent variable x on the horizontal axis, so here's our year, and our dependent variable, movie attendance, is going to go on our vertical axis. Dependent always goes on the y-axis, the vertical axis. Independent always goes on the x-axis, the horizontal axis. And make sure when you're choosing your scales, make sure you choose a scale that goes up by an even amount each time. So attendance, notice that I should have a break in here because I skipped some values, but after that skipped values between 0 and 80, it goes up by a constant amount each time. It goes up by 5 each time. It's important that your scale goes up by an even amount each time. And years, I started in 1994 and went up by an even number of years each time, by 1 year for each unit. And why did I choose 80 to start at for attendance? Well, I needed, my lowest value is 83.8, my highest value is 125.6, so I needed a scale that goes at least between those ranges. So I started at 80, and then I went all the way up to 145 because I'm going to be making some estimations later on this graph. And years, I started at 94, and I went up to 2006 because later we're going to be making an estimation for a year outside of our range. So if you plot all of your points on this graph, so this is going to represent a point on the graph, this is going to represent a point on the graph, and so on. So in 1994, movie attendance was 83.8 million. So in 1994, 83.8 would be roughly right about here. I would put a dot at that point right there. In 1995, movie attendance was 87.3 million. So I would put a dot at about 87.3, which is right about there, and so on. If we put a point for all of our data values and then draw a line that shows the trend in the data, you would have something that looks like this. I have my break in my graph there. And it would follow roughly a linear trend. When you draw a trend line, make sure you follow two rules. Make sure your line goes through as many points as possible, and the points that it doesn't go through, like here, 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 are evenly distributed above and below the line. So there's 3 above the line, 3 below the line. But make sure you draw your line that goes through as many as possible. The ones that doesn't go through, evenly distributed above and below, and you'll have a good trend line. The trend line does not have to start at the origin. It can start anywhere along the y-axis, anywhere along the x-axis, just as long as it follows the general trend in the data. Now we can use that trend line to make estimations, but first, let's describe the correlation between year and attendance. I would want to describe it in two ways. First of all, since our line is going up to the right, we say it's a positive correlation. And since all the dots are fairly close to the line, we say it's a strong correlation. So it's a strong positive correlation we have here. So up to the right is positive, and the dots are close to the line, so strong. So it's a strong positive linear correlation. And what that tells us is that as the year increases, the movie attendance is also increasing. And now notice from our data table, there's no data for 2001. So we want to make an estimation. We want to make an estimation for the movie attendance using our line of best fit. So in 2001, we go up to see where does 2001 meet our line of best fit. It meets it right here. We look across on our y-axis. That's about right here. So that's about 121 million would be our estimation for the year 2001. So you make sure you're using your line of best fit properly here. So 121 million. And then we also have to know, was this estimation something we call an interpolation or was it an extrapolation? So what's the difference between the two? If we look at the data we're originally given, we're given data between 94 and 2003. That's the range of our data. It goes all the way from 1994 to 2003. If we make an estimation for a year between our lowest and our highest year, we call that an interpolation. If we make an estimation that's outside of our range, so either less than 94 or bigger than 2003, we call that an extrapolation. So we made an estimation for 2001. That's between 94 and 2003, so we call that an interpolation. Let's make an estimation for 2005. So if we look at our line of best fit, so 2005 is here, see where our line of best fit says the attendance would be for 2005. So we put a point on our line of best fit at 2005 and then look across to the y-axis. It's about right here, about 143 or 144. I'm going to say my estimation is about 143. Remember, we're in millions. Here, did we use interpolation or extrapolation? Well, 2005 is outside of the range of data we're originally given. It's bigger than our highest value, 2003. So we say that that is, in fact, an extrapolation. Okay, next thing you would have done would be distance time graphs. How do we analyze a distance time graph? Describe motion. Well, here I have a distance time graph, and if we read here, it says, describe the following graph that represents a person's distance from home over a period of time. So we have a period of time of 7 minutes, and the graph tells us the distance the person is in meters from their house during that period of time. So at the very beginning of the graph, when 0 minutes have elapsed, they're 0 meters from their house, which means they're at their house. But then 2 minutes later, we'll notice they are 100 meters from their house. So this rising line up to the right tells us the person is moving away from their house. Right? If they were 0 meters away from their house and now they're 100 meters away from their house, they must be moving away from their house. So this rising line up to the right, that tells us movement away from the center, or in this case, away from the person's house. So any line moving up to the right is movement away. And since it's a straight line with no curves, we say they're moving away at a constant rate. And I'm going to say this is a slow movement compared to the next line segment because it takes 2 minutes to travel 100 meters in this line segment, but this line segment here from B to C, 2 minutes later, they've traveled 300 meters. So they traveled 300 meters in the same amount of time it took them to travel 100 meters. So BC is a faster movement. And you can tell the difference between fast and slow because faster movement is a steeper line. Slower movement is a less steep line. So let's describe the motion here of line segment A, B. So up to the right, which means away from the house. And we're going to say at a slow, steady pace. Steady pace means that the speed is constant. They're not changing speeds. They're not accelerating or decelerating. And BC, the line is still going up to the right, but it's steeper. They're traveling a further distance in the same amount of time, so they're moving faster. So we'll say they're moving at a fast, steady pace away from their house. So away from home at a fast, steady pace. How about CD? Line segment CD. At the beginning, so at 4 minutes, they're 400 meters away from their house. And then 2 minutes later, at 6 minutes, they're still 400 meters away from their house. And the line didn't go up or down at all between those two. So the person must not have moved at all. So for 2 minutes, they didn't move. So any horizontal line represents no movement. So in this case, CD, no movement. DE is the only line segment going down to the right. So they were 400 meters away from their house, but now they're only, at the end of the line segment, they're only 200 meters away from their house. So they must be moving towards their house. Any line segment going down to the right represents movement towards the sensor, in this case, towards the person's house. And it's a steep line, so they're moving fast towards their house. And there's no curves, so it's at a steady rate, a constant speed. So line segment DE, we would say the person is moving at a fast, steady pace toward home. And in distance time graphs, be careful to look for curves. If you have a curved line, you have either an acceleration or a deceleration. You have an acceleration if the line starts off not very steep, but then gets steeper and steeper and steeper and steeper and steeper. That means their rate of movement is increasing, so that'd be an acceleration. If we have a line that starts off very steep and then gets less steep and less steep and less steep and less steep as we move from left to right, that represents a deceleration. So be careful of that when we're doing distance time graphs. Okay, the main section for linear relations you would have looked at is the y equals mx plus b section. Basically, if we have two variables that form a perfect linear relationship, that happens when as one variable increases, we have another variable that increases at a constant rate. So one variable is a constant multiple of the other variable. So this equation you would have learned what all these variables mean, and specifically you would have learned that m represents the slope or rate of change. Actually, I have that written right below, rate of change, or called the constant of variation. B represents the y-intercept, graphically speaking, or the initial value. And we have y and x, right, because we have our two variables that have a relationship between the two, y being our dependent, you know that, x being our independent. So if we have two variables that form a linear relationship, where one variable is a constant multiple of the other variable, we say m is the rate of change between those two variables. And if we have a table of data, we can calculate m, the rate of change, by figuring out what is y changing by, divide that by what x is changing by. If we have a graph, we can figure out the rate of change by counting our rise and dividing it by our run. And in an equation, you'll refer to m as the slope or rate of change or constant of variation. So what we're going to do in this section is be able to work between the table, graph, and equation forms of a linear relationship. But before we do that, let me just quickly show you what I'm talking about here. So if we have a relationship here between distance and time, so the distance traveled by a bus varies directly with time. So we have distance and time as our two variables. Distance depends on time, so distance is y, time is x. It says the bus travels 240 kilometers in 3 hours, so our distance and our time once again. It travels 240 in 3 hours, but if we want to figure out the rate of change, or the slope, or constant variation, whatever you want to call it, if we want to figure out the rate of change, we want to figure out what is the distance changing by for every 1 hour. So to calculate that, we call it our m. Our rate of change is m. We do our change in y, which is 240, and in this case, kilometers. And we divide it by our change in x, our independent variable, which is time, so 3 hours. If we do this division, it'll tell us how many kilometers the bus travels for every 1 hour, and that's our rate of change. We always need to know what is y changing by for every 1 unit increase in x. So 240 divided by 3, that gives us 80 kilometers per hour. So the bus is going 80 kilometers per hour. That's our m, that's our rate of change. Okay, another thing you would have looked at before I get into more specific things about linear relations is you would have looked at the difference between direct variation and partial variation relationships. So there's two types of linear relationships. It could be a direct variation relationship where the initial value is 0, 0 for the relationship between the variables, meaning graphically the line that represents the relationship between two variables would pass through the origin. And in the equation, you don't see anything added after the variable x. There's nothing added off at the end here. You could write a plus 0 if you want to, but that's a direct variation relationship. Initial value of 0 passes through the origin. The equation has nothing added at the end here. You don't see a plus b because the b value is 0. The y-intercept is 0. Partial variation relationship has an initial value that is not 0. So when x is 0, y is something else. In this case, I gave an example of y being 1 when x is 0. That means, graphically speaking, the line is not going to pass through the origin. In this case, it's going to pass through 1. In the equation, you're going to see that y-intercept, that initial value, added after the x. And we call that a partial variation relationship. So what we're going to do now, we're going to be able to, given a linear relationship between two variables, we're going to be able to represent that relationship between the variables in a table of values. We're going to be able to represent the relationship using an equation, and we're going to represent the relationship between the two variables using a graph. So let me quickly show you those three things, and then we'll work at moving between those three things. So cost due to electrical work varies directly with time, so it tells us it's a direct variation, and it's the relationship between cost and time. And in this case, cost depends on time, so cost is dependent, time is independent. They charge $25 per hour. It tells us how much it costs for every 1 hour, so we know our rate of change. We know our m value is 25 in this case through electrical work. If we want to show this relationship in a table, right, in a table we put x on the left, y on the right, and remember x is time, so they could do work for 0, 1, 2, 3, and we can make this table as big as we want. I'm going to stop there. Those are our hours. Now, how much would it cost for each amount of these hours for them to do work? Well, if they don't work, it's not going to cost anything. If they work for 1 hour, since they charge $25 per hour, it's going to cost $25. If they work for 2 hours, it's going to cost $50, right? It's 25 bucks per hour, so 2 times 25 is 50. If they work for 3 hours, 3 times 25 is 75. It would cost $75, and so on. This shows the relationship between cost and time for this electrical company. We could represent all these numbers with one equation. We can make an equation that shows the relationship between x and y. In a direct variation relationship, the equation is always y equals mx. Any linear relationship is y equals mx plus b, but you'll see why we don't need the plus b for this equation, because the initial value for this equation, the cost when x is 0, is 0. So we don't need the plus b because b is 0 in this case. The initial value, the y-intercept, is 0. So the relationship between cost, remember y is cost, x is time, cost is equal to $25, that's our rate of change, times the amount of time they do work for. And this equation shows us the relationship between y and x for any value of x, right? If we wanted to figure out how much it costs for them to do 3 hours of work, you plug in 3 into our equation for x, 25 times 3 is 75. We get cost equals $75. If we want to figure out how much it costs for them to do 10 hours of work, you would plug in 10 for x, and we'd get cost equals $250, and so on. Now, graphically speaking, if we were to plot these points on our graph, let's see what it would look like. 0 hours of work costs $0, 1 hour of work costs $25, 2 hours costs $50, 3 hours costs $75. Notice how this is going up by a constant amount each time. That's what makes this a linear relationship, because the rate of change is constant. And then we would connect these points with a line to show the relationship. And there's the graph of the relationship between cost and time for these two variables. So we could represent the relationship between cost and time in 3 different ways here. In a graph, using an equation, or in a table of values. All 3 of those ways show the relationship between cost and time for this electric company. And notice this is a direct variation because it starts at 0, 0 and goes up by a constant amount each time. That makes it that makes it a direct variation. Also, we have a plus 0 here that also shows us it's a direct variation. And from a table, we know it's a direct variation because the initial value is 0, 0. Okay, let's look at what if I gave you just a table. We don't know what x and y are here. We know x's are independent, y's are dependent. We don't know exactly what they are. We have a table of values here. What if I wanted to come up with an equation to represent the relationship between x and y here? What I'm going to need for any linear relationship equation, it's always going to be the form y equals mx plus b. I'm always going to need to determine what is the value of m and what is the value of b to be able to write the equation of the relationship between x and y. So what I'm going to do first is I'm going to figure out the value of b. That's the easiest thing to figure out. The value of b, that is our initial value, or you'll hear it referred to graphically as the y-intercept. The y-intercept, so that means where does it cross the y-axis? So when x is 0, what is y? So I'm just going to write that here. When x equals 0, y equals what? And we can get that from our table. When x is 0, y is 4. So our y-intercept, our b value, our initial value, b, is equal to 4. So you just look in your table. When x is 0, what's y? That's your initial value. That's your y-intercept. If we were to plot this point 0, 4, that would be right on the y-axis, which makes our line cross the y-axis at 4. So that's our b value. M, how do we figure out m from a table of values? Well, remember I showed you equations before. To figure out your rate of change, you're going to have to figure out what is y changing by and divide that by what x is changing by. And that will tell you for every 1 unit increase in x, what is y changing by. So to figure out the change in y, an organized way to do it is to do your second y value minus your first y value and divide that by, to figure out your change in x, do your second x value minus your first x value. So y2 minus y1 over x2 minus x1. That will tell you your change in y divided by your change in x. Now you have to pick 2 points to be your first and second points. I'm just going to choose the first 2 points for it to be simple here. So this is my first point, 0, 4. So that's my first x value, my first y value. I'll choose this as my second point. So this is my second x value, my second y value. If I plug those values into my equation, I have 8 minus 4 over 2 minus 0, and I get 4 over 2, which is 2. So my m value is 2, my b value is 4. I can write my equation by plugging in m and b into y equals mx plus b, and I get y equals 2x plus 4. This equation shows the relationship between x and y. And notice this equation works, right? If I plugged in 8 for x into this equation, what should I get my answer for y to be? It should be 20. 2 times 8 is 16 plus 4 is 20. It shows the relationship between the two variables. Now I just want to point out, you didn't have to choose this is your first point, this is your second point when you plugged into y2 minus y1 over x2 minus x1. Let's say we could have chosen any 2 points. I could have chosen this one to be my second point, x2, y2. If I plugged into my equation here, I would get 16 minus 4 over 6 minus 0. And that would give me 12 over 6, which is still the same answer of 2. So that's how to go from a table to the equation. What if I give you an equation, I want you to draw the graph? Well, to be able to do that, we know 2 things from our equation here. M, we call that, graphically speaking, we call that our slope. M equals slope, which in this case is 3, and any whole number is over 1. And we're talking about slope. Remember, the top is our change in y. I'm going to call that rise. And the bottom is our change in x. We call that run. But where do I start from? Don't forget this here. That is our y-intercept. That's our initial value. So we know our graph starts right here on the y-axis at -2. And then from there, I need to use my slope of 3 over 1 to plot more points. So that means rise 3, run 1. So remember, a positive rise means up. A positive run means right. So up 3, right 1. And then continue. Up 3, right 1. Up 3, right 1. And to plot points on the other side of the line, do the opposite of up 3, right 1, which is down 3, left 1. And we get more points on the same line. Connect. All the points should be on the line if you've done it properly. And that's how to go from the equation to the graph. Plot your y-intercept. So use your b value to plot your y-intercept. Then use your slope. Use the rise and the run. The numerator is the rise, the denominator is the run. For rise, counting up is positive. Counting to the right is positive for run. If we had a negative rise, we would count down. If we had a negative run, we would count left, and so on. What if we wanted to go from a graph to the equation? Well, there's a couple ways we can do this. We know our equation is y equals mx plus b, and we know we're going to need to figure out the values of m and b. So b is the easier one to find, right? B is just the y-intercept. It tells us when x is 0, what's y. So where does it cross the y-axis? It crosses the y-axis right there at 2. So my b value is 2. But to calculate the rate of change, we have a couple options. We could choose 2 lattice points, so points in the corners of the boxes, and we could count our rise and our run, right? M equals rise over run, graphically speaking. So count your rise to get from one point to the other. We would have to count up 1, 2, 3, 4. Up is positive, so positive 4 is our rise, and then we'd have to go to the right 1, 2. Going to the right is a positive run, so 4 over 2, which is 2. That's fine. But what if you wanted to go from, instead of going from here to here, what if we wanted to go from here to here? We would have to count down 1, 2, 3, 4. So that would be -4 as our rise, and then we would have to go left 2, which would make it -2 as our run. Notice, same answer. Negative divided by negative is positive. Doesn't matter which point you go from, you'll get the same answer either way. Also, you could use the method we used before, using our change in y over change in x, which is y2 minus y1 over x2 minus x1. That works perfectly fine as well. Change in y is the same as rise. Change in x is the same as run. We could just choose our 2 points here. Let's say this is our first point, so that's our x1, y1. Here's our second point, x2, y2. Plug into our equation. We get 6 minus 2 over 2 minus 0. Sorry, 6 minus 2 over 2 minus 0. That gives us 4 over 2, which is 2. So either way, you get the answer of 2 for m. Plug into your equation y equals mx plus b, and we get y equals 2x plus 2. This equation shows the relation between x and y for this graph. We're going to do some equations of lines algebraically quickly, and then we'll be done this section. So before we do that, you have to remember parallel lines, lines in the same plane that never meet. Parallel lines have equivalent slopes. So you have to remember that parallel lines have equivalent slopes. Perpendicular lines, lines that meet at 90 degrees, have slopes that are negative reciprocals of each other. So you have to remember that, negative reciprocals of each other, and I'll explain that more in a second. So determine the equation of a line algebraically given different information. I could give you slope, remember slope is m, and one point it passes through. So I didn't give you the y-intercept. To find the equation of a line you always need two things. You always need slope, y-intercept. I gave you slope, I didn't give you y-intercept. You can use this point. Remember, every point has an x and a y, and the equation of a line will satisfy x and y for any point that's on the line. So what we can do is use this information, m, x, and y, plug that in for m, x, and y in our equation, and then solve for b. So if we do that, if I plug in 5 for y, -1/2 for m, -4 for x, into y equals mx plus b. So I'll have something that looks like this, -1/2, -4 plus b, solve for b. I will then know the b value. I can write my equation by plugging in for m and b. So I'm just going to solve this quickly. -1 times -4 is 4, so I would have 4/2. I know that 4 divided by 2 is 2, so I can just write that as 2 plus b. Move the 2 over, becomes a -2. 5 minus 2 is 3, so I have 3 equals b. So my final equation, I plug in for m and for b. I have -1/2x plus 3. How about here? What if I give you a point and I tell you it's parallel to this line? Well, we know parallel lines have equivalent slopes, and the slope of this line, the number in front of the x, is a 1. So I have a parallel slope is 1. Those two lines are parallel. That's a symbol for parallel. Parallel slope is 1. And I have a point on the line, x and y. I can use the x, the y, and the m, plug into y equals mx plus b, and solve for b. Remember, so y equals mx plus b. -4 is y. 1 is m. X is 4. Solve for b. So -4 equals 4 plus b. Move this 4 over. -4 minus 4 is -8. So my final answer, y equals 1x minus 8. So we know parallel lines have equivalent slopes. They don't have the same y-intercept, so don't use that at all. All we know, parallel lines have equivalent slopes, so I can use the slope from that line along with the point we know is on our parallel line. Plug it all in, solve for b. There's the equation of our line. How about perpendicular lines? So we know our line goes through this point, and it's perpendicular to this line here. So perpendicular lines have slopes that are negative reciprocals. So this slope is -2/5. A perpendicular slope, there's a symbol for perpendicular. Perpendicular slope, we flip the slope. So instead of 2/5, we make it 5/2, and we change the sign. Instead of it being negative, we make it positive. So we have a perpendicular slope. We have a point. We don't use this y-intercept at all. All we know are perpendicular perpendicular lines have slopes that are negative reciprocals. So we use that perpendicular slope and that point. Plug into y equals mx plus b and solve for b. So y is 0. M we know is 5/2. And x is 5. And we don't know b. If we solve this equation, 25/2 plus b. And, sorry, last step here, move that 25/2 to the other side. We get -25/2 equals b. So my equation of my perpendicular line, I use my perpendicular slope, 5/2. X minus 25/2. That's the equation of a line that's perpendicular to this line and goes through that point. The only other way I could ask you to find the equation of a line would be if I don't give you the slope or the y-intercept, right? We need both. We need m and b. What if I don't give you either? But I do give you 2 points the line goes through. There's only one line that goes through these 2 points, and we'd have to start by finding m, by figuring out our change in y, so y2 minus y1, over our change in x, x2 minus x1. So if this is our first point, that's our x1, y1. This is our second point, that's our x2, y2. Plug into our equation. Be careful with your signs. We have to do 4 minus -2 over 6 minus 4. And if we do this, we get 6/2, which is 3. So my slope is 3, so I know m. I'm going to now, next step, into y equals mx plus b. I can plug in my m, and I can choose either of these points to be my x and y. Let's just choose the first one here. This is my x and my y, so y is -2, m is 3, and my x is 4. And then we can solve for b. -2 equals 12 plus b. And we would get, if we move the 12 over -2 minus 12 is -14 is b. So the equation of my line, y equals 3x minus 14 when I plug in m and b that I solved for. And you didn't have to choose this point. You could have chosen this point to be your x and y here. You would have gotten the exact same answer. The only other thing from this section, it would be horizontal and vertical lines. Let me just very quickly review this. If you have an equation that looks like this, y equals a number, you don't see an x at all. What that is, that's a horizontal line that crosses through 2 on the y-axis. So you would just draw a line, perfectly horizontal, that crosses through 2 on the y-axis. That's the line y equals 2. The slope of all horizontal lines is 0, and the y-intercept in this case is 2. Why is the equation y equals 2? So just very briefly, notice that every single point on this line has a y-coordinate of 2. It never goes up or down, right? This is point 6, 2. This is point -8, 2. Every single y-coordinate of every point on this line is 2. That's why we say the equation line is y equals 2. How about an equation that says x equals a number? You don't see a y. Well, that's actually a vertical line that crosses through 3 on the x-axis. So we would just draw a vertical line that crosses through 3 on the x-axis, and that is the line x equals 3. The slope of all vertical lines is undefined. And the y-intercept, well, it never crosses the y-axis, so we would say none. Why is the equation x equals 3 for this? Well, notice every single point on this line, right, this is point 36. This is point -6. Sorry. This is point 3, -6. Sorry. This is point 3, -6. This is point 3, -2. Notice that the x-coordinate for every point on this line is 3, so we call the line x equals 3. X equals a number is a vertical line, y equals a number is a horizontal line. Slope of horizontal lines is 0, slope of vertical lines is undefined. Alright, so that's it for linear relations. Make sure you watch part 3 geometry, and then you'll have done all of grade 9 math.